We, as Glenn mentioned, we had an ARM projects. This is the Advanced Robotics and Manufacturing Institute out of Pittsburgh. We've had this is a follow-on to a project we had kind of the year leading up to when Hammer started, and then we got this follow-on. Glenn said Brian Thurston was on the team. My colleague Adam Bynack here in the Ames lab was on the team, and so we've demonstrated now an incremental robotic forging system with integrated heating that can actually heat up steel. And so I'll show you a little video here. This is an hour-long forging session that we've sped up to 20x. So you're going to see a 3-minute video of some steel getting real hot and getting smashed around. And so I'll ramble while the video is going. So I'll just go ahead and start it up here. You're going to see the robot come in, and it's sort of putting this part inside of the induction coil. You can see it already getting hot. Again, this is 20x, but it's about 5 minutes is the initial heat. So that when this thing pulls out, that was 5 minutes. After that, the heats aren't nearly as long. You've got a couple views over here where you're seeing perpendicular to the press, and then kind of down the end of the press, or sort of looking down the rod geometry here. And so you can start to see, we're getting it real hot, and you can really see the volume change. We take a 7-inch long, 2.5-inch diameter billet, and we lengthen it to a little over 12 inches. So we get almost a 2x elongation. You can really see that material starting to stretch there. We cog the geometry down from that 2.5 inches to something as a little bit smaller than 1.5 inches in the sort of narrowest region. So getting a significant amount of deformation. This is a sort of little totem pole geometry. It's to mimic an Air Force part that Glenn's talked about numerous times, the sort of tie rod geometry that they've been interested in. The tie rod's kind of boring. It's just a cylindrical round rod. So we wanted to do a little more than that. So we've got a rod geometry, but we put different cross sections in. So we have a sort of square cross section, an octagon, diamond, a round, and then we've kind of put a paddle on the end of it. Brian's got a CAD file that he'll share here in just a second when the video's over to show you what we were trying to make. You'll see a picture of the final part here at the very end before we show the CAD file. So again, this whole thing takes sort of an hour to go completely run automatically. We're sort of only just sitting there with our hand on the e-stop in case it decides to try to hurt somebody. But otherwise, nothing really going on. I will draw attention to this kind of crazy looking space contraption that's on the end of the robot. This is a compliance device that Brian designed that allows us to have sort of compression and tension sort of compliance. It can also twist and rotate. So when we put these big forces on the part, it sort of protects the robot, and it works beautifully. And so it helps with set downs. And so this is really like the blacksmith's wrist, and the robot kind of becomes the elbow and the shoulder and the waist. So we gain some degrees of freedom there with this compliance device. So we're almost done here. I think there's about 15 more seconds, and then it's going to show the part at the end. You'll see me do a little cleanup on it. Yep, right here. So this is what we were trying to make. See, like any good video, we clean up after ourselves there. And then I'm going to stop sharing, and Brian's going to show you the CAD of the actual part we were trying to make. I don't know if we have a picture of them sitting side by side. I do in the presentation, but just for reference, that's what we were trying to make. You should see on your screen now. And we did some quick miking measurements, and we're within 2 to 4 millimeters in all sort of key dimensions on this part. So it would be pretty easy to throw this thing into a machining center and clean off basically the scale that's formed and get it to the geometry. And Brian's done some cool work on writing some code to sort of create templates for cast preforms. So if you know where you're trying to go, how do we cast something that's really close to where you want to go, and then just add a little bit more deformation. So that was part of the project as well. So we're really excited with the progress, and we're sort of ready to start smashing other things that have been made with other processes to really lean into the hybrid part of our hybrid autonomous manufacturing that is Hammer. I don't know if there are any questions, if anybody wants to dig into any of that, but we had a good time.
Mm-hmm. Yeah, I was in the room for a bit of this, and it is great seeing big machines work, things going red hot and all of that. And And again, this has value. The shapes like this you could make by additive manufacturing. It takes an awfully long time. And then it's a really efficient way of changing shapes for machining later. And I think we need to get into some cost modeling and so forth, but I'm sure there are significant savings that we can realize there. So thank you, Mike. And yeah, great job to the team over there. Really foundational stuff that so far as I know is nothing like this has ever really been done before, as simple as it is.
Yeah, I think it opens the door at this point to at least like, so we haven't dug into the, let's call it the more science side of things. ARM is really focused on like making parts and transitioning technology now. But now that we have this system, I think people want to ask questions about how does microstructure evolve during these processes? How do we control things? There's a lot of control opportunities on this press right now. Most things here are fairly open loop. So we've got a really nice test bed that if anybody wants to sort of collaborate and play, happy to talk.
And it does span research and engineering, and there's a lot of basic science. So it's exactly what an ERC is supposed to be doing. So thank you. And maybe we'll have some more open discussion at the end. I do want to keep us moving on to what is the main course. Ben Armstrong and Bruce Crothers, who's our resident sociologist within the program, and one of the areas we've got to we have to keep in mind with Hammer is going to introduce Ben. So I'll hand it over to you, Bruce.
Thanks, Glenn. So yeah, I'm Bruce Carruthers. I'm the resident social scientist, and today's talk is going to be something different. Normally, we hear presentations about engineering things and some of the science, and sometimes we hear from some of the companies. And today, Glenn and I agreed that it would be interesting to have somebody like Ben Armstrong present, because Ben is someone who really does research and is very mindful of a lot of what's happening downstream. So after after you engineers have invented these amazing things that can forge and have be sort of digital blacksmiths, eventually the hope is at some point those new technologies are going to be adopted in a workplace, and they're going to lead to changes in how American manufacturing works. They're going to change work processes. They're going to involve demands on a new kind of workforce. They're going to have implications for the old workforce, and that is really the space for social science. And last year, as I was starting to kind of read the literature, the state of the art on the kind of social science of work and manufacturing, I stumbled across this huge project that was run out of MIT called the Work of the Future Project, but it turns out involved a bunch of economists and political scientists and other social scientists, many of whom I knew. And I thought, well, this is interesting that these people are all generating this big investigation. And of course, there's the glamorous, famous, economists and whatnot. And then there's the people who actually do the real work. And it turns out Ben is one of those people who's been very centrally involved in the Work of the Future Project, but who continues to be involved in some really interesting stuff that's happening at MIT. And so thanks to Glenn, I reached out to Ben, and Ben was agreeable to sort of give us a state of the art on what's going on when we start to move robots from the lab to an actual manufacturing firm. So Ben Armstrong, welcome to Hammer, Ben. He is the executive director of the Industrial Performance Center at MIT. He was trained as a political scientist. He got his PhD from MIT, and he actually was a Northwestern undergrad, it turns out. So I knew there was something I liked about that guy. But in addition to those many other virtues, he's got a really good cutting edge sense of what kind of work, what can social science tell us about what happens when these new forms of artificial intelligence and robotics start to enter actual functioning workplaces, and where robots are being adopted and implemented by big firms, by small firms. What happens then? And that, of course, is one of the things that at Hammer we're very interested in because of all of the work on the relationships with community colleges and technical institutes and thinking what are the workforce demands and implications of all the stuff that we're trying to do. So that was probably a little bit more long-winded, but I'd like to welcome Ben Armstrong. And Ben, the floor is going to be yours. And then afterwards, I'd like to curate the Q&A, and hopefully we'll have a good, lively discussion, because really this is something quite different from our usual main course. So Ben, please, welcome.
Yeah, thanks so much, Bruce. I really appreciate the introduction and just some context on the type of work we do, where the data that I'll show you comes from. You know, our group at MIT has been around for more than 30 years now, and we got started in the late 80s out of a project, a multidisciplinary project, engineers and social scientists, which we still have the same kind of composition now, focused on U.S. manufacturing competitiveness in the face of growing Japanese competition, particularly Toyota, Japanese mini mills, et cetera. And what the initial work product that came out of that group that would later become the center that I now run was a book called Made in America. And what's interesting is looking back to that book from the late 80s, there are a lot of interesting lessons from research, both in engineering and social science, that we never really, lessons that we never really implemented. So a lot of our work now is following up on those, some of those 30-year-old ideas about how manufacturing in the U.S. might begin to compete. One is a new approach to workforce development. Another is increased technology adoption, more scheduled capital outlays like the Germans do, that type of thing. So happy to talk about kind of how the group has evolved, but also, in those 30 years, we made different connections with large and small businesses, mostly manufacturing. And we have relationships that allow our students to go and visit and gather data on the new technologies that these firms are adopting, but also to have data sets on the customers of technology providers like robots. So I'll focus today largely on robotic automation, but we could talk about other types of automation as well. And I'll show you some data from both the universe of industrial robots, but also from a particular collaborative robot manufacturer that helps us dig into exactly what the challenges are in terms of using automation technologies to improve productivity and worker performance. So to dig into it, I want to start with, just a quick case comparison. And as Bruce knows, in the social sciences, sometimes we love cases, most similar cases, companies, in this case, that you might expect to be performing very similarly, but actually they look quite different. So when I want to anonymize these companies for a moment, call them Alpha and Beta. And these are two real companies in Ohio. Both have robots on the factory floor. They're, I would say, relatively advanced in how they think about both machining technology, but also machine tending technology. And they're relatively similar in other ways too. They're only about 10 miles away from one another. The CEOs are friends socially. Slight difference in size, but mostly both small firms, under 100 people. Both defense contractors. One more on the aerospace side. The other has a mix of parts in terms of arms and aerospace, and both really traditional SMEs in the sense that they have a wide variety of SKUs that they build, but they mostly produce those parts at a low volume or highly variable volume. And then in terms of revenue, that's where we start to see the difference. So Beta, which is about half the size of Alpha in terms of employees, is producing over 50% more revenue. So the productivity of Beta is really, vastly outperforming Alpha. They're both aware of this. It's still a puzzle. How exactly has Beta been able to scale its production to a productivity level that some really large factories don't even achieve, while Alpha has been relatively stagnant. And I should say here that Alpha isn't a story of failure here. It's more of a story of what the median firm of about 50 employees looks like in the aerospace industry. So we started out looking at this question by interviewing folks at Alpha and Beta, doing site visits, trying to understand how these companies worked. And one of the hypotheses that we came in with was that when we talked to Alpha, They said they have a ton of demand for new parts that they want to build. Their CEO even says that they could double in size overnight if they wanted to, but they can't find workers to actually scale up to double in size. So that led us to the question, could there be some kind of skills gap? Why can't Alpha find the workers that it needs? And when we look at the broader data around Alpha's industry and its region, we do find that workforce issues are a real thing. So here's data from a survey of MEPs, so manufacturing extension partnerships around the country, and MEPs have this survey that they've been deploying for the last more than 20 years. And the survey asks a consistent question, what are your top 3 challenges as a small and medium manufacturer over time? And as you can see from these lines, most of those challenges have been relatively stable over the last decade. And the one challenge that's really been changing is this orange line that you could see growing from about 20% of respondents to about 60% of respondents. And that's the challenge of recruiting and retaining a skilled workforce is the language in the survey. So clearly SMEs, Alpha is not alone in its challenge recruiting skilled workers. And of course, in the administrative data, we know that during COVID, you could see this green line spiking. That's job openings in manufacturing. But what I want to point your attention to is that it wasn't just after 2020 that job openings were spiking. There was actually about a tripling in the scale of job openings between 2010 and 2018, the same time that SMEs were really crying out that, hey, workforce issues are beginning to be a bigger and bigger concern. So we looked at this data. We talked to companies like Alpha, more than 50 of them, and we found an interesting pattern of what's evolved over time. That as overall employment in manufacturing declined, most of that decline was between 1980 and 2010. Between 2010 and 2020, this period where job openings are growing, there's also an increased demand for manufacturing employment. Manufacturing employment is going up about 12%, but the interest in manufacturing jobs and the skill development programs to support the manufacturing workforce are really becoming more and more scarce. So what you get companies starting to do is they adopt a new workforce strategy, which is they say, we're going to hire for will and train for skill. We're not actually going to look for people with the skills we need because we think those people will be too expensive. So we're going to start people in lower wage jobs, and then we're going to develop internal training systems to really help them adapt. And the challenge with this is the following. So you see that these firms are starting to try to develop skills in-house. Not only aren't they equipped to develop internal workforce programs, any real training that they do would have to take a skilled employee off the line or away from their spindle to focus on training the more junior employee. But we also see that manufacturing jobs during this period become noticeably worse in terms of their wages compared to other jobs. So I want to focus on this plot of the manufacturing workforce. Pretty simple plot, but there's an important story here. So if we look, this is a plot of average hourly wages for the gray line is manufacturing workers, so direct labor in manufacturing, factory workers nationally, and the green, and I should say this is manufacturing workers without a college degree. The green line is all other workers outside of manufacturing without a college degree. And what this shows is, of course, in 1960, a manufacturing job on a factory floor is a very good job. It pays on average 40% more for someone who comes out of high school versus someone who comes out of high school into a factory job versus someone who comes out of high school into a different job. But over time, you see that this premium of going into manufacturing shrinks such that today it's only about 2%. So it goes from being about a 40% premium to about a 2% premium. And that a lot of that shrinkage has come as manufacturing jobs have become more and more scarce, and you've seen a shift to this hire for will, train for skill behavior. So there does seem to be a race to the bottom in this type of wage behavior. You've seen a lot of manufacturing jobs move to the South and Southeast, which is a lower wage market. So there are a variety of forces that are kind of driving this decrease in wage premium. And you can see that in the map here, right? So it's not uniform that the manufacturing wage premium is 2%. In my state, home state of Massachusetts, it's actually negative. So workers out of high school could make more on average in non-manufacturing careers than manufacturing careers. Same goes for North Carolina, Florida, California. But in Ohio, Michigan, Wisconsin, there is still a slightly higher manufacturing premium on the order of 5 to 10%. Nonetheless, it still is a huge issue that over time, manufacturing jobs have become less good in terms of the wages, the additional wages they offer the workers. Now, during the same period, and this is a story that you'll be familiar with in this group, there's been a shift in demand for manufacturing labor from the factory floor to engineering offices, right? So the engineering content of manufactured goods has become higher, and there has been a demand for engineering jobs in manufacturing that do pay a very good wage. Most of those jobs are, of course, available only to those with college degrees. I could share more about this in Q&A, but there's actually, in some states, this middle band of states that you'll see, like the Dakotas down to Oklahoma, where the manufacturing wage premium is still very high, on the order of 20%. They also have a high share of manufacturing engineers who don't need a college degree. So there's a whole different type of manufacturing workforce in those states that I think is a model for other parts of the country. Okay, so getting back to the alpha and beta story here. So one of the interesting conclusions that Alpha comes to, and not all, I would say, SME manufacturers have come to this conclusion, is that, hey, we have all this business that we could be doing, but we can't find workers to fulfill that business. And what we need, we realize we're paying too low to recruit the right workers to meet demand. So we need to raise wages. But we can't really justify paying workers $20, $25 an hour at our current productivity levels. So we need to become more productive. That means we need to automate. So really, it was a worker shortage challenge that led a firm like Alpha to automate. And what they did first was, of course, they buy a robot, and they think that, okay, if we buy a robot on the factory floor, this is a factory with, I would say 20 plus machining centers. And they think currently we have one operator to maybe 2 machines. If we buy a robot, maybe we can go 1 operator to 3 machines or 1 operator to 4 machines, directly contributing to increased productivity. So this is what they try. And what they find is that it's much harder than it looks. Initially, they hire an integrator. The integrator comes and they put in fixtures to essentially install universal robot arms, collaborative robot arms on a large set, I think it was about 10 machining centers. And they try out with one robot arm. They call it Jeff because they want the employees to welcome it as kind of a teammate. And they think that they're going to promote a collaborative relationship where the robot manages to load and unload the part and set it up for quality inspection. And the operator becomes more of a supervisory control role, where this is someone who's supervising an automated system, a cell, and ensuring that in identifying incremental improvements to that cell consistent with the lean methodology that this firm adopts. And that was the plan. And what I can say is that Jeff is no longer working at the firm. Jeff is in the corner, last I checked, and not operating, nor have the other machining centers been set up with robot arms. And this is I would say, not uncommon story. And I'll get into some of the numbers in a second. And seeing things like this, I work with robotics engineers who are really puzzled why the robots that they've, in many cases, contributed to designing, the robotic systems that have improved in performance and speed over time, why they often fail to succeed in environments like this is a real puzzle. And that's one that we've been trying to unpack. So I'm going to share data for the rest of the presentation on that puzzle in particular. So the first picture that I'll say is that, Alpha's not an anomaly, that overall what we've seen is that, the wages in manufacturing, like I mentioned with the wage premium, have been relatively flat, but also the red line in this figure, capital expenditures among manufacturers adjusted for inflation, those capital expenditures, investments in new technology were going up from about 1960 to the early 1980s with a boom in investments in early numerically controlled machining. Again, you saw a big boom in investment in the late 90s around investments in computing. But since about 2000, the CapEx among manufacturers has been flat. And so has value added of U.S. manufacturers, and so has wages. So this is a really, I would say, doomsday story for U.S. manufacturing. And really, it's a story of the manufacturing doldrums of the last 20 years, the flat blue, red, and pink lines. And all this to say that specific technology investment among U.S. manufacturers has been quite low. So the most advanced technologies, ranging from industrial robots to cloud computing to even specialized equipment, the adoption, and this is a national survey of manufacturers of all sizes, adoption's been very low. That you only find any robots at all in 1 out of 8 factories. You don't find many digital capabilities in factories with under, let's say, 500 people. And then when you look at job postings for manufacturing workers. This is a data set of over 1 million job postings. You see that the job postings for production workers are far less likely than other job postings to require any digital skills at all. And this includes, like from reading a spreadsheet to doing, machine learning type work or algorithmic work. It's that production jobs, it's a hire for will, train for skill, no relevant skill requirements to digital work. And I want to suggest that this has been a long-standing challenge, and not just in the United States. So here's International Federation of Robotics data on robot adoption over time. This is similar. I would say capital equipment overall has been increasing in places like Japan and Germany, where it's flatter in the United States. But in terms of robot adoption, what was really striking is that even in a period of high manufacturing demand like 2020 and an acute labor shortage, you saw robot adoption in the US, Germany, and Japan all go down, which I think is really striking and cause for concern. The China numbers here might not be surprising given widespread national subsidies for robots in China. The government has made robot adoption very cheap, but what we see from ethnographic studies, and I'll highlight the middle quote here from a sociologist, Yao Wenlei at Harvard. When researchers have gone into factories in China to try to understand how robots are performing, they see a picture that's much like Alpha, where these companies bought robots because they were very cheap and they thought that they would be able to help with electronic assembly. But as you'll see from the quote, we've tried to make robots assemble components, and then the ellipsis here is that the robots often break the components. They're not dexterous or sensitive enough to manage these type of electronic assembly tasks. So they end up going back and relying on humans. There have been other high-profile cases of, I would say, failed large-scale automation projects, including Tesla's first Model 3 factory. And then at the bottom, we have a quote from a company that we studied in Germany, which the CEO mentioned to my colleagues, that his goal was not a lights-out factory where not just individual machines, but a whole set of machines could run without any human intervention. He thought that type of process would reduce the level of innovation, because the innovation still really came from his human workers observing processes and working to improve them over time. So, of course, we see individual machining centers or cells running lights out or running on a third shift unattended, but we see a lot of human intervention, even in the highest performing, most automated factories, that are contributing a lot to incremental innovation in those contexts. So from a lot of this work, both the data and the observations, we've come to a few conclusions, and we've written about this, about why automation seems to be so hard, particularly robotic automation. Part of this is a design challenge that many robots currently in the field today in manufacturing environments, there's this trade-off between their reliability and their flexibility. They have to be very reliable to do high throughput, high volume tasks, but that when they're programmed to be so reliable, it's very difficult to adapt to either slight changes in the environment or changes in the manufacturing process. So there ends up being a skill-intensive and high-cost process to adapt the technology to meet when the process changes. And finally, one of the things that I think makes small manufacturers like Alpha resistant to these changes is that the robot's often a black box, and you can't really explain why it's giving you the error code that it's giving you, and it's very difficult in many cases to troubleshoot if you don't have that robotics engineering background that a lot of factory floor workers who are interacting with these robots don't. So making those systems more transparent is certainly an objective for the engineers that work in our group. Now, we have this story of Alpha, where they faced a lot of challenges with automation. Now I want to tell the story of Beta, where they have some kind of robotic automation with every machine in their shop, and they've seen huge productivity benefits. And what I'll say is that in the economics literature, they're actually there's now widespread evidence from Finland, from Canada, from the United States, from, I think, the Netherlands as well, that when firms like Beta actually adopt robots at scale, or even software automation at scale, they end up hiring more people, becoming more productive and more competitive in their industry. So contrary to the story of scaling up automation is a story of worker displacement, actually what we see is these positive returns. Sometimes the hiring and growth is in different types of occupations. It's not just hiring more factory floor workers, for example, because of course you're getting more productivity out of your operators. But sometimes you might hire more managers or more engineers. Nonetheless, overall employment does tend to go up on average in the robot adopters. So let me dig a little bit into this beta story, and I'll give you just a note on methodology. You know, one approach that we've taken is to look at the companies that are the high performers. So those companies that are in the 1 out of 8 that actually buy a lot of automation technologies and work backward from them. And another is to kind of go forward and go out to firms and just try to understand from the ground up how they make their technology decisions and try to map those decisions over time. But most of what I'll give you today is the big picture data. And what we have here, excuse me, from multiple data sources, is kind of a decision tree for firms as they adopt. I'm mapping robotic technologies in particular, but we can do this with a few different automation technologies. So roughly, it depends on the data source. 10% of all firms buy, they do some kind of automation experiment with one robot, and then about half of those firms buy a second robot, and many of those firms that buy a second robot end up scaling up further. And we say that those firms are in a higher technology, higher wage equilibrium, because a lot of times the necessary skills to operate an automated system are associated with higher wages for those on the factory floor. So there's a higher wage premium in those cases. I should mention for Beta that the average wage at Beta is, or the wage floor at Beta is about $30 an hour compared to the $15 to $18 an hour at Alpha. So it's not just more automation, more jobs, it's also higher wages. Now, what I want to focus on for a moment here is this decision of how to scale. Why does Beta follow the top line, whereas Alpha follow the bottom in the 4%? So I can say from a high level, this varies a lot by industry, and what many of you who have either worked in manufacturing or know the various sub-industries well, is there's huge variation. And in many ways, pharmaceutical manufacturing is so different than automotive manufacturing. It's weird that we call both manufacturing, but still, in the national data on robot adoption, about 50% of all robots are in automotive factories. What I think is interesting is a lot of those robots are quite old or have been there for a long time. So in terms of productivity, the automotive industry in the US has not really become more productive in the last decade. It's pretty much kind of flatlined. Similarly, that when you look at the UAW negotiations, wages have been flat, but productivity among production workers has also been pretty flat, largely because the boom in CapEx in the automotive industry and the robot adoption was a little while ago. But what we've seen in more movement is in electronics and then the metals and kind of machine shop centers that I know some of you are really interested in. And what I want to note here is that if you look at column 3 and column 4, you see, of course, that metals is actually employing more people in the United States than automotive, but has a far lower share of automation by a few different measures. However, there has been a big move toward adopting collaborative robots, particularly for machine tending in kind of the metals and machine shop world. Similarly, in electronics, there's a higher share, at least by comparison to the overall robot adoption among cobots. So this has led us to really dig into this cobot data, where we have a much richer sense of who's adopting and what's their adoption patterns over time. And we find, I think, some really interesting results around repeat robot purchases. So I want to focus here. The left column is robot adoption as a share of overall robot sales. So this is just in collaborative robots here. And then column 3, what you'll find is that there's this pretty high variability in terms of second robot purchases, that in pharma and in auto, second robot purchases are actually pretty high by comparison. But in the metals industry, a lot of firms like Alpha are buying one robot, but they're not buying a second. And another way of visualizing this, I'm going to skip ahead for a second, is looking at the number of robots sold. And this is just logged on the x-axis, and then the probability of a repeat purchase on the y. So you see that I don't know why this is. Okay. You see this outlier to the right, which is the dyad of metals industry robots used for machine tending. So this is the case of Alpha, where you see the highest number of robots sold for that industry and application, but actually a pretty middling, even if on the low end, of repeat purchases. So this application is clearly a problem, whereas there are other cases, like for robots for assembly or for material handling, where there are fewer robots overall sold, but a lot more repeat purchases. So this is kind of an indicator of where some of the problem applications might be that we've been focusing on more over time. And what I want to suggest overall, and this is just some more of an aside for some of you who are working on building the industry ecosystem for Hammer, what we find is there's some suggestive evidence that there's a network effect here, that if you have a firm, either an OEM in your region and you're one of their suppliers, or you see maybe a firm down the street adopting these types of robots, we see kind of a knock-on effect. So here's just a plot of collaborative robot purchases in Columbus, Indiana over time. You could see there's one company here in about mid 2018 that buys two in quick succession, and then a large company that buys. Those of you know Columbus, Indiana, you know that there's one very large company, Cummins Engine, that is dominant here. And what happens is that even though there's about a year or two between robot purchases, after the kind of two anchor companies buy, there's actually a surge in purchases and actually scale up from a few other firms. And the data we have is anonymized, but kind of the story that I think is, the hypothesis that comes out of this is that it could be that there's some network effect of large companies in a region transferring knowledge to suppliers who are then investing more in capital equipment, and that it's not just a random process. There's another hypothesis out there from some economists that it's actually integrators that end up shopping around robot solutions to firms in an industry, and the integrator is kind of the key link that can lead to more technology adoption in a region. And it's still unclear how exactly that happens, but there is some regional clustering that's happening in terms of the adoption story. So this kind of, just to bring it back for a second to the alpha beta comparison, what we have is a story of much higher productivity at beta, much higher wages, and that's a story that's been enabled by automation, and essentially beta figuring out how to scale up their automation. And one of the things that I think I've showed that the beta story is somewhat anomalous. Only about 6% of firms overall, a much smaller share of firms beta size, have been able to do this. But I haven't really shown how they did it. Right? It's unclear. Like, what would you do if you wanted to replicate the beta story? If you wanted to promote scale up at an SME like that, and one of the things that I have found really striking about beta that they've done is they have restructured their workforce. So rather than just take existing operators and essentially added a robot alongside them, really what beta did was they transformed what the role of the operator was and what skills were required. So the head of beta is actually an instructor at a local workforce development program who has helped essentially redesign the curriculum for what it means to be a technician on the manufacturing floor, how to essentially program new technology, debug automation solutions, and think about ways to digitize the factory floor. So not only has he introduced these, a robot in every spindle, he's also introduced machine metrics and other tools to essentially monitor how well the robot's performing and to be able to measure any performance improvements. So he's restructured work to essentially say that his operators are responsible not just for ensuring, essentially babysitting the machine, babysitting, not my word, but the word that a lot of these SMEs use for kind of the lower order operator. But it's really for understanding how you can make this system perform optimally. So not only has he changed the role of the operator to be this more supervisory control role, he's also changed the compensation structure for the role. So I mentioned $30 an hour at the bottom end. What he's done effectively is to measure the output of each worker at each machine using machine metrics, so that the more the more efficient your machining center is, the bigger your bonus. So he has the baseline that each worker needs to hit, I think is 85% capacity, as they've measured capacity. And then any worker who, you know, gets above 85, the margin you're above 85 is directly related to your bonus. So he has these individual workers who are rotating among machines. They have the kind of more the Toyota production system philosophy of cross-training and switching work. You know, they're able to measure, and the workers have taken home big bonuses that are proportionate to their increases in productivity. So just to link this to the chart on the screen here, he's taken the role from more of a classic operator, where at the national level you make between $15 and $20, to something that looks more like a technician, which at the national level is a rarer job, but pays much more and typically requires more training and education. So to summarize, we have alpha, where you're taking a technology and you're layering it on an existing production system. You're not really transforming the underlying process or the underlying system, whereas beta is not only reorganizing the process to welcome in automation, it's also reorganizing work and the skills required to perform that work, which is helping drive both productivity gains, but also wage gains. I will leave it there. I might point you to some of our writing on this. I'm happy to link it through Bruce that can give you more detail. But really, the framework that comes out of studying firms like Beta that we think is necessary to think about how you scale automation technologies, we call positive sum automation, meaning automation that is both can enhance the productivity of firms while also increasing the flexibility of those firms to adapt to different circumstances, but also a high mix of products like many SMEs face. So I'm happy to take questions and dive deeper into anything that was mentioned, but really appreciate the opportunity to speak to the group, and a big fan of what I've heard of your work.
Well, thank you, Ben. And for those who are interested in following up, Ben co-authored a terrific article in the Harvard Business Review earlier this year. So I can commend that to you if you want to kind of remind yourself or see in printed form some of the ideas that he presented. And it's written for a broad audience, so it's a pretty non-technical article. So one of the things, just to offer my own quick reaction, I think for Hammer, one of the great things that Hammer is already doing is partnering with educational institutions and thinking about skill level and new skills for the workforce. And I think one of Ben's messages is that's a good thing to double down on. Really pay attention there. There's some real opportunities there. Some new opportunities that maybe Ben calls our attention to is to think, well, geez, if we want to diffuse these technologies, let's identify who are the integrators in an industry, because they could be the sort of carriers. They could be they could help diffuse, or think about partnering with a large firm with the hope or expectation that what happened in Indiana might happen, which is the large firm adopts the new technology, and then they put a little pressure on their suppliers and the folks that are in their local industrial ecosystem. So you could be quite strategic about your partnerships in the industry and kind of move this diffusion process forward. And then finally, I think the three characteristics that Ben identified are really worth us thinking about, which is think about the external environment. Don't just focus on the technology. Think about the environment for the technology and how easily your technology can be adapted to different sorts of environments. So, as it were, think outside the box. Then think very much about what kind of skills are required to program and to maintain these technologies. And are there some very high skill demands? Is it the sort of technology that can be operated by very clever graduate students in a lab, or could you put it out there and have some blue collar shop floor workers plausibly learn how to maintain or troubleshoot these new technologies? That's a real important issue. And then finally, the whole issue of black boxes are tough to deal with. How to induce more transparency, and that's where there's some interesting tensions between the IP aspect of the Hammer project, and how much to share and how transparent to make these technologies. But I think that's another thing that's worth thinking about. So thank you very much, Ben, and definitely, folks, follow up with that Harvard Business Review article if you want to hear some more. Now, if you want to raise your hands, I'll call on people to ask questions. But I know I've heard already from Stefania Peroni, who's on the among us. And Stefania, why don't you ask your question? And you need to turn your camera on or somehow unmute yourself. There she is. Okay.
Hello.
Stefania,
Hi.
please go ahead.
Yeah, so I've read some papers about this topic, and I've learned that, as you said, small firms have more, especially high mix, low volume, have more difficulties in adopting new technologies. So my question is this fact that small firms have more difficulties in adopting new technologies actually a problem, or is just how the situation is and it's not a problem? And if it's a problem, why? I mean, which are the bad consequences of this difference between small and big firms?
So there's a gap between small and large factories in terms of technology adoption, and that gap's grown over time. So it didn't always exist, I think, is the first thing to say. And part of the challenges around the consolidation of U.S. firms, but also the movement of low value added manufacturing overseas, starting in the 80s, but accelerating in the early 2000s. So there's a lot of kind of like geopolitical factors about why this gap has increased. But I got started in studying this in part because the DoD was really concerned about the lack of technological capabilities at small and medium manufacturers. So I was working with the manufacturing technology group at DoD, which is saying, hey, we have a large base of our, a large share of our defense industrial base that's producing really critical goods, but they're way behind the times. What's going on? And is this a problem for our competitiveness? And what we concluded was that it's a problem for a few reasons. One is that if smaller firms can't actually improve their productivity, so small firms have been flat with their productivity or declining for the past 10 years. So that's problem number one. Like if you're not improving your productivity, you're not gonna be able to compete. And the DoD is concerned about that because if they can't compete in commercial markets, they're gonna be more dependent upon the DoD to maintain their business. That could be more expensive for DoD. So that problem number one is just a productivity problem, that if you're not acquiring new technology, you're not improving your productivity, and you're not gonna be able to compete in the global economy. Problem two about lower technology adoption is incompatibility between buyers and suppliers. So a lot of large firms, we talk to defense OEMs, but we also talk to others that are frustrated in part because ideally they would have some kind of call it a digital thread, call it whatever types of compatibility, so that the manufacturing process the OEM wanted the supplier to follow was possible, whether it's robotic welding of a certain kind, or to meet certain standards of certain tolerances. So they, in some cases, DoD primes have told their suppliers, you need to buy this equipment. We will help you finance this equipment because you need to be able to meet the standards that we're looking for, and the new standards we're looking for in this part. So part of it is just the basic competitiveness problem, which is really what motivates us. Like these companies are not becoming more competitive, and they're just going to die off if they don't invest more in new technologies. And then the second problem is this incompatibility that really is a problem for the supply chain. What I could say about the competitiveness point that it might be interesting to the Ohio folks is when we started this, we're like, okay, maybe this is a DoD problem. This is like there's something weird about the defense industrial base. So we looked at a data set of companies, small and medium manufacturers in the defense industrial base. And then we compared them to this universe of small and medium manufacturers overall. And what we found is in one data set of Ohio small and medium manufacturers, over 40% of them had at least one defense contract. So there's this really huge overlap between, the SME community and those with defense contracts. And what I see that as a really troubling sign, because it means that, maybe you can't compete in global markets. And now you're just, looking more and more for these high margin defense contracts that can keep you in business. So if that's one thing that, as I've talked about with DoD, is like should be very worrying, and you want a healthier, more competitive industrial base, so that could produce higher technology goods for defense purposes in the future.
Okay, thanks.
Anyone else? Yeah, Glenn, please.
I'm muted. I'm just wondering if you go back in history a little bit, if there was a similar thing that happened with CNC machining, where we went from manual to CNC, and it seems to me in that case it would be almost impossible to compete very long unless you adopted, the invested in the technology and upped your productivity. And that, I think automation robots is kind of another level of complexity, another level of black boxness, and another level of the problems with interoperability than you had with CNC machining.
Yeah, and I don't want to. I mean, part of the point, I think, Glenn, could be like, hey, the market's going to take care of this, right? Like, you're either going to adopt this stuff or you're not going to be in business, and let's wait 10 years and it's going to kind of settle it. And what I worry about is that with certain, protectionist forces, or certain, what we think of like technology lock-in is the term we would use, is that some firms are they have a lot of either intellectual property or customer relationships in a certain area that they are able to kind of, corner a market, but not necessarily adapt with their manufacturing processes. And, you could, again, with the DoD example, you could see the US getting really behind in some industries because it ends up propping up these SMEs that don't adopt new technologies. But then SMEs in the supply chains, mostly in East Asia, you can imagine SMEs in China that are growing far more rapidly in their manufacturing processes. So I would expect the same thing around the diffusion of CNCs. That's just a market issue. One of the funny things that we noticed about early CNC adoption is that companies didn't want to do it. Like their workers didn't want it. Like early NCs after World War II were like, no one wants to adopt this technology. So what happened was, it was the Navy. No, it was actually the Army. So the Army initially, essentially, gave out NC machines to their suppliers that you need to use this, and they ended up kind of pushing this technology out to the industrial base, even though they didn't want it, and said, no, this is a condition of working with us, is to use this equipment, which is just better for quality reasons. So that type of diffusion is just not the market mediated process that I would have expected.
Yeah, actually, I mean, just to follow up on that, I think, that's a great example of the fact that, if you have one very large, powerful customer, and in this case, the DoD, but it could be a very large firm, a very large OEM, they can induce change that wouldn't otherwise spontaneously happen, basically using their leverage over their own suppliers. So if you want to think about how to diffuse these technologies, each marketplace, each industry has got its own kind of structure of big players and small players and alpha males and feeder institutions, and that kind of structure can give you a sense of where if you're going to make a special effort to diffuse a technology, where's a strategic place to start, because from there you might be able to reach others, and that kind of big size disparity between a buyer and a set of customers is one place to look. Rob, you got your hand up. Please go ahead.
Well, Glenn's going to come and visit us here in the next week or so. And I guess I'd have to say, Ben, I'm not exactly sure where you are geographically. I guess you're probably, if you're at MIT, you're Boston, I guess. But I have so many things going through my head and listening to your conversation here, that I have to invite you to come and visit us. I think that's the only way to do it, because I think that, we've looked at going down this path with a Ford shop, and there are certain structural limitations that are very different than if you're trying to put a robot on a CNC machining center. And I think maybe you need to appreciate some of those kinds of barriers. And I could just say, for instance, I would love to spend $250,000 on a robot and not on health insurance. Okay, there's an example. I would love to spend $250,000 on a robot and not have to rebuild my forging press for $750,000. But I got to rebuild the forging press because when it breaks, I'm out of business. So there are little things like that in our overall trying to stay in business that I'm not sure that they're quite in your calculations. And I think maybe you need to see some things going on in the forging industry to understand some of the kinds of issues that are going to come up in hammer. So just saying, that's my comment. You know, I'll chat you my email address, and you know, maybe I'll see you sometime soon.
Yeah, you know, we love to, you know, we're visiting you know, a factory that we work with on Monday. We love to bring students out and all go visit. So that'd be great. And I don't mean to say this in a totally generalizable way, Rob. You know, we work with you know, like the wood processing industry we've worked with, and, you know, like a lot of different industries where, you know, robots just aren't relevant, for example. It's just not a, you know, this technology, you know, they're looking for other ways to enhance productivity, whether it's with, you know, other types of specialized equipment or whatever it might be. So I don't want to make this sweeping statement that, you know, if you haven't adopted a robot, you're somehow, you know, that's not, nor do I want to actually criticize Alpha, because I think a lot of Alpha's responses to this technology are legitimate. And they're a profitable business, you know, so they're not going anywhere, right? But they're finding a way to be profitable with very slow productivity gains, and they're not really capitalizing on a lot of the opportunity that there is in their industry right now. Like, you know, like I mentioned, they said they could double their revenues with existing customers, but they just can't do it for workforce reasons and technology reasons. So I think that's very interesting when we're talking about at a national level and getting to the policy conversation, you know, that manufacturing is important to the future of the American economy for national defense reasons, for middle wage jobs reasons, you know, that I do think there's a lot of potential, untapped potential in manufacturers. And of course that varies by industry and application. And Rob, just in response to what you said, which I think is, you know, now saying, I think the empathetic thing, I'm going to say maybe a controversial and not very empathetic thing. You know, when I've been talking to the DoD about this, you know, one thing that I've emphasized is that for the last 40 years, so since we really started to recognize that U.S. manufacturing was in decline, was losing a step competitively, our main focus of the MEP program, of, you know, job retraining programs, has been to essentially soften the blow for small and medium manufacturers. So large manufacturers helped create the problem by moving their supply chains overseas, and then the federal government's role has been to try to improve the competitiveness of companies like Alpha. And those policies have failed. There's no evidence that those policies have been successful at scale in improving competitiveness. So the argument is that we need to try something different this time if we're going to compete. And what I suggest in terms of what we need to do that's different is improve, you know, incentivize a lot of, you know, innovative capital expenditures. So expenditures in new equipment that requires new skills, and really reward that type of behavior, both in startups, but also in existing companies, and put competitive pressure on companies like Alpha to accelerate the process that Glenn's talking about. Like, if you don't adopt this technology, you're just not going to compete. So that's the role that I think that policy can play here. That's quite different from the role in the past. You know, a final note, and I know we're over time now. You know, one thing I'll mention on the large company level, about 40% of the large factories in the last, I would say since about 2008, about 40% of new billion-dollar factory investments have been from foreign companies. So there's a lot of foreign company interest in investing in the United States. And one of the challenges of those, you know, opportunities and challenges of those foreign companies is they come in with a different production process, often a different workforce strategy. And oftentimes they come in, and this is just what the data says, they come in far more productive than their American peers. So, you know, whether it's TSMC coming into Arizona, or, you know, Toyota a long time ago coming into Kentucky, there are these new processes and these new ideas and new approaches to technology that I think American firms can really learn from and benefit from. And we've seen a lot of variability in whether the knowledge of those foreign companies actually spills over into their American counterparts. So I think that that's another opportunity for kind of learning and improvement for American firms as well.
Well, thank you, Ben. And it is time. We've had a really stimulating hour and a great appetizer and a robust main course. And so I think we got to bring things to a close. So thank you all Hammer participants. It's been a great 2023, and I guess I'll see you all next year. And a special thanks to Ben Armstrong for really showcasing a whole bunch of work that is, telling the Hammer audience about some interesting things that happen after the invention in the lab. How do we get out there in the real world, and what kind of situations and trends do we face when we think about moving these things into the real world? So thanks very much, Ben. Thanks, Glenn, and thanks for the video of that hot device in the lab that was busy forging and pounding, and I love the heavy metal quality to some of our talks. So see you, everyone.
Hey, great holiday. See you all. January 18th is I think our next one, and see you then. And yeah, Ben, thank you very much. That was spot on, the kind of message that we need, and it's a lot of challenges out there that we need to, we want to be part of the solution to. So all needs to come together: the policy, the technology, awareness of what everybody's facing. So thanks so much.
Thanks, everyone.